So the last thing we're going to look at in our study of series and sequences is this thing called the infinite geometric series. And I've talked about this a little bit, hinted at it on previous lessons. And so now we're going to get into the details. And the idea is that if my value of r is less than 1 in magnitude, then every time I multiply, I'm going to end up getting a smaller number. And if I add those together, my sum increases, but it increases more slowly as I go along and eventually levels off at a number. And so let's see if we can illustrate that in a way that's easy to understand. What I'm going to do is take this sheet of paper. Okay, so just imagine this is a piece of paper, and I'm going to just cut along these lines here. And so when I first cut along this line right here, I start with a piece of paper that's half of a sheet, and I have my other half over here. I'm going to cut again here, and that gives me a half plus a quarter. And then I cut that piece in half, and that gives me an eighth. So I have a half plus a quarter plus an eighth. I take the remaining sheet, cut that in half, that gives me a 16th. Cut that in half, I get a 32nd. Cut that in half, I get a 64th. In half, 1 over 128. It's getting too small to write here. This is 1 over 256 for this half. This half is 1 over 512. Oh my goodness. It just keeps going, and it keeps going, and it keeps going. I keep cutting this thing in half, and I can't even show, but it's going to be an infinite number of cuts, because every time I cut something in half, I still have half left over. So no matter how many times I cut it, there's still a little piece left. So what do we have here? We have a geometric series, a sequence rather, that goes 1 half, 1 quarter, 1 eighth, 1 16th, and so on. A sub 1 is equal to 1 half. R is equal to 1 half. That's what we're multiplying by each time. We're cutting this paper into half. And n actually goes to infinity. Okay, we can keep cutting this as long as we got scissors small enough and paper we can cut this an infinite number of times. Well, what happens if we add all this up? If we add up all of these pieces, we end up with one sheet of paper. So the sum of 1 half plus 1 quarter plus 1 eighth plus 1 16th plus 1 32 plus 1 64th plus 1 28 and so on, the sum of all of those fractions is 1. The infinite number of fractions, the sum is equal to 1. And so if and only if the value of r in magnitude, okay, and we can use the absolute value to get the magnitude, if the absolute value of r is less than 1, this series, this sum, is going to converge to an actual number. Okay, if I add up from 1 all the way to infinity. Okay, if I add every term in this sequence, going on and on forever, I actually get a single number, and this is the formula that I get. A sub 1 divided by 1 minus r. Probably the simplest formula we have so far, and the most complicated situation. So as long as the magnitude of r is less than 1, my series is going to converge to a number. If r is greater than 1 in magnitude, the series diverges and no sum exists. That means it grows forever. So you saw a lot of those sequences where, for example, with the rabbits, right, where as we went farther into the sequence, we got bigger and bigger and bigger numbers, and they just grow unbounded forever. So if we look at this in terms of a finite geometric sequence, we can get the partial sum of the series up to some number. For example, n equals 3. So if I take the first 3 sheets of paper, first 3 pieces of the paper, and add them up, what do I get? So in this case, we would use our formula of a sub 1 times 1 minus r to the third power divided by 1 minus r. And if we do that, we end up getting 0.875, which is 7/8. We get 7/8 of a piece. So we're actually getting pretty close to 1 already with just a few terms. If we keep going and we stop at n equals 8 to see what our total is, we would have 1/2 times 1 minus 1/2 to the 8th power divided by 1 minus 1/2, and that gives us 0.9961 of a piece of paper, and that's rounded off. There's some more digits after that. And then finally, what happens if we go out to 100? Well, if we plug this in, we get the same formula, 1 minus 1/2 to the 100th power divided by 1 minus 1/2. And if you plug that into the calculator, you're going to get something that looks like equal to 1. And we know that it's actually something that's 0.999999 and so on, because it's got to be slightly less than 1. We haven't added one little tiny piece that we could still cut in half, but it's a very, very, very small piece. So we're pretty close to 1 in this case. Okay, so let's try a couple of sort of random examples here. In each case here, we see that this is an infinite sum, and so we want to use the formula a sub 1 divided by 1 minus r to calculate this. And so in this case, we're going to plug in a sub 1 is 12, and we're going to divide by 1 minus negative 1/2, and this gives us 8. Okay? Now notice that r is less in magnitude than 1. So the absolute value of negative 1/2 is positive 1/2, and that is less than 1. Okay? So we would expect this to converge to 8. Okay? How about here? Well, we don't really want to do anything because absolute value of 4 is greater than 1, and we know that this is going to just continue to grow forever. And so we would say this sum diverges, and that would be it. We'd be done. If we go down here, let's skip down to this one here, we see that this is also less than 1. So negative 2 in absolute value is less than 1. I'm sorry, is greater than 1. What am I talking about? Negative 2 is greater than 1. And so this also diverges. And there's nothing to calculate. Okay, we just know it grows forever. Here I have r equals 1/3. And 1/3 is definitely less than 1. And so we can go ahead and apply the formula. A sub 1 is negative 3. Okay, that's this part right here. And we're going to divide by 1 minus 1/3. And when we do that, we end up getting, I'll put an equal sign there, we end up getting negative 4.5. So if we add up all infinity terms of this sequence, we end up with negative 4.5.